today, keeping in mind that it's probably also going to be helpful to go through the next steps. The idea of having the factorization theorem in QCD as I presented yesterday, I said yesterday it was essentially the same idea, the same spirit, the same logic as what you would have in renormalization. And I'd like maybe to repeat that statement just again as an introduction to today's lecture. So if you essentially think about this as Alex would do in his effective theory lectures, where you do have the UV at the far top and the UV at the far top and the infrared at the far bottom and looking at scales. Imagine you're trying to do renormalization. What renormalization tells you is that if you're trying to measure, say, physics at some scale, some hard scale, I'm still thinking about high energy scales here, Q, and you try to renormalize, to compute things in perturbative, whichever QED, QCD, probably also all sorts of BSM theories. At some point, you get UV divergences, okay? And what renormalization tells you is that you can always reabsorb those divergences here, so something bad happens somewhere really at zero distance, in a way. And you can always reabsorb those divergences in a way that at the end of the day, your coupling masses and everything your physical coupling masses and all parameters are finite, and you are able to write down whichever cross-section at the scale Q or whichever process as a function of, say, alpha E at the scale Q and so on and so forth, okay? And by reabsorbing those divergences, you're essentially saying everything that happens at infinity there, you can always introduce some cut somewhere. That's what people usually say, it's the renormalization scale. And everything that happens above the renormalization scale is hidden into alpha E at the renormalization scale. Alpha E in that case, yes. And by essentially taking that scale, identifying those two scales, I can actually work at this scale in my problem. But anyway, the idea here is saying I can hide all the details that happen there if they're BSM physics or if there's anything else far above that scale. In a way, I don't care. I can always reabsorb it into the definition of my parameters and then live with that and do perturbative calculations at the scale of interest, okay? And by saying that the physics should be independent of this specific choice of scale, you do get a renormalization group equation that tells you how these parameters vary, all right? So in a way, it's really saying I don't really care too much about what precise details of physics are physically going to regularize my theory there, if there's even a need for that. The idea behind trying to understand particle distribution functions for the protons is the same, but upside down. So you would, instead of having a divergence in the UV, you do have a divergence somewhere in the infrared, so at soft scale, and then there's the same question. If you have something that diverges in infrared, does that mean that I have to worry, and now if I want to do anything, if I'm working now at a hard scale Q, do I have to work out what are all the non-perturbative, gory kind of details of the proton, or can I live without worrying about that? And the idea here is exactly the same. You will introduce some factorization scale, so that's what usually people call μf, which I failed to mention yesterday, and you're going to say all the details of what happens below μf at scale lower than μf, I can just put all those details under the rug and hide them inside the distributions of my PDFs that I will define at a scale μf. And once I've hidden everything here, if I want to measure, say, F2 at this scale here, I can always write F2 depending on Q of X and Q squared. And the same way as in, and unfortunately Alex, I think, is not going to cover this in his lectures, but the same way that when you introduce something like that, you should probably match the theory above and below. In this case, F2 can be written as, well, if the exact expression for F2, and that's something I failed to mention yesterday, so I will mention it now. You can write F2, which was X EQ squared, let me take single flavor. You can actually always write it down this way. I'll explain this in just 1 second. Times Q of Xi and Q squared in this case. So what you're doing here is saying essentially, once I've defined, the same way that once you've defined alpha electromagnetic here, you can write the cross-section in series of alpha s here. What I'm doing here is once I've hidden all the details of the soft scale in my Partial distribution function, I can always just write f2 as a function of my PDFs. And by this expression, these things are essentially the matching coefficients between the two, which can be themselves expanded in series of alpha s. Okay? Generally speaking, if you go to alpha squared, for example, you can have a diagram where you would interact like this. And in that case, F2 obviously depends on the definition of your proton. At alpha s, at alpha squared, this can have a finite term in alpha s, okay? All right, but the logic is the same, again, except that now what we're saying is that if I want to do some perturbative physics here, I can. Because once I've defined this object, which includes all the things I don't want to have to deal with, I'm fine. And again, imposing that physics is independent of the choice of mu f is going to give you same kind of equation as the one you have for the renormalization of the couplings, and give you the way with which PDF depends on the choice of scale. Okay? Is that clear to everyone? And the same way that you know that the standard model is renormalizable, so that procedure can be carried on order by order, perturbatively renormalizable, order by order in perturbation theory, there's a theorem that tells you that this thing can be done at order alpha s to the 10 if you're willing to sit down and compute both coefficient functions and splitting functions and splitting kernels at alpha s to the 10. Okay? May take some time, but it's doable. Okay? So, what I will do today and tomorrow is moving to what probably everyone is finally expecting, which is hadron-hadron collisions. I hope that's what you're expecting. So the logic behind this lecture and tomorrow's lecture is trying to first, as I did for the earlier lecture, first gives you a brief overview of the basic ingredients and the basic concepts. Then thanks for submitting many suggestions for the extra topics I wanted to discuss. There's, I'd say, 1 and 2 half winners. The one winner, that was actually not what I would have expected, but okay, that's nice. The one topic that had the more votes were trying to discuss on-order calculations. So I'll try, and I'll explain try in a second, I'll try to discuss this in more detail tomorrow by explicitly doing a simple resum calculation. Don't expect something too fancy, but at least just to highlight. I will do a calculation. I will get my hands dirty for this. Also, some people had requested to discuss amplitudes and event generators. I'll briefly do that in today's lectures, and maybe tomorrow, depending on time. That's what I mean by try. I'm actually not sure exactly where this is going. For the other topics, what were the other ones? I think there were a few people requesting jet substructure. I probably won't have the time to cover this. I just sent to the organizers a list of references that I promised. In that list of references, there's essentially some handwritten copies of these notes, and there's also all sorts of references for all the other topics. Resummation is not something for which there are so many references, so it's mostly lecture notes I found here and there. Amplitude is a topic per se for which there are beautiful detailed lecture notes. So if you want to get your hands dirty, which I won't, it's something that you can easily look for. For Monte Carlo generators, I also tried to give you a few introductions by authors of main generators. And for jet substructure, you'll have to wait. We're actually with a few people trying to write a series of lecture notes by ourselves, and should be done by the end of the month. So if anyone wants, the document is ready mostly. It's mostly typos to be fixing. So if anyone is interested, since I will not cover it, just send me an email. I'll send you a copy of the PDF we have at the moment. So, proton, unless there's any question. No? Good. Well, good. I don't know. If there's any question, you know where to find me, right? So I'm actually going to go back to what I just erased. In E plus E minus, in DIS, we just wrote yesterday, or well, we just wrote 5 seconds ago, that you can always try to write down F2 as a sum over all flavor, some integration with some hard coefficient times some, let me call Fi here. Fi can be either quarks or gluons, that's the Parton distribution functions, of some psi and some scale q squared. So that's essentially telling you that you do have a set of PDF with D-lab evolution that hides the details of non-perturbative effects, and with some evolution that fixes the q-square dependence from perturbative QCD, and some coefficients here, which are essentially the hard matrix elements. It's really saying, the way to interpret this is that if I'm scattering a photon of a proton, I can really factorize some hard coefficient which interacts either with a quark or gluon here with some quark distribution function. Well, I can really take outside of the proton, if I can put it that way, maybe that's cleaner, some quark or gluon here, which does interact with my photon. So I've really factorized long-distance physics from a hard coefficient function, which is soft. That's in the sense in which it's a factorization formula. Can we do the same in proton-proton collisions? So this lecture now, that's the end of DIS. We're discussing about proton-proton, or more generally, hadron-hadron collision, although PP or PP bar is all I'm going to talk about. Can we do the same? It's tempting, right? How would you do that? So remember, the logic here is essentially saying I can take a quark or a gluon out of the proton and have it interact with the photon. All right? Can you do this? How would you do the same in a proton-proton collision? You do the same twice. So you're going to say, and this is probably where things are going to get ugly at some point in the lectures. I have a proton here. Let me do that the opposite way around. I have a proton here. I have a proton there, coming each of them from their own side, and that's the beam direction. That proton here is going to get me, let me do a quark here, and a gluon on this side. I'm going to get one quark from the proton, one quark from one proton, one gluon from the other, and these guys are going to interact and give me whatever you want. Okay, and give me, I don't know, gluons, quarks, W, Z, whatever you want. Quark can be top quarks, can do Higgs, can do BSM particles, whatever this is going to give me. At some point, it's coming from a hard interaction, and we know, or we at least expect, that because of QCD factorization theorems, if I go to high enough scales, at some point I can hide all gory details of physics inside the PDFs and live with something which is just here a hard matrix element, some coefficient that I can compute in perturbative QCD. All right. So the master formula here would really be that whichever cross section or differential cross section you want to measure, you're always going to be able to write it down as a sum over all flavors A and B of the possible incoming partons. I need more space to do this, and okay. An integration of, well, each of the quark and each of the incoming partons here can carry whichever fraction you want of the proton energy. So say from proton 1 I'm taking a fraction x1, from proton 2 I'm taking a fraction f2. I have PDF A of x1, PDF B of x2, and at the end of the day, I just have to compute perturbatively a partonic cross-section or a partonic matrix element, which depends on x1, x2, well, which in principle does not depend too much on x1 and x2, depending on what happens. But so let me forget about this dependence for the moment. So I have to find a partonic cross section here, which will depend. Well, let's say it depends on x1 and x2, generically speaking. Usually through a combination of these variables, but let's leave this aside from the moment. What other dependencies do I have? Well, obviously, I need to specify some factorization scale if I want to get the PDFs. The PDF obviously also depends on alpha S. And alpha S has to be taken at some renormalization scale. And this, of course, is also going to depend potentially on mu f. If mu f is widely different from the scale of your problem, you're potentially going to get logs of mu f over whichever hard scale q you get, mu r, and obviously alpha s as well. So, leave aside all these dependencies for the moment. I'll come back to that in hopefully later. The main thing here is, again, we've written some factorized expression. I've put all the gory details in the infrared inside the PDF of the proton on the left and the PDF of the proton on the right. And at the end of the day, once I know PDFs, which I can just borrow from deep inelastic scattering. So let's assume we have at the moment done some good deep inelastic measurements and that we know the PDFs of the proton. Once you have that, the only thing you're left with is just being able to compute this matrix element for producing whichever high energy final state you're interested in from an incoming set of two partons, okay? So this is again a very basic pocket formula that is the heart of any calculation at the LHC at the moment. When you hear that people try to do calculation at leading order, next to leading order, next to next leading order, this is the basic formula where you want to stick your guys. There's one little, depending on how serious you are, little or big, depending on how serious you are, caveat here. The factorization, this is proven, any order of QCD. Modulo corrections, which are actually power suppressed in 1 over q squared, so up to corrections which are, so if you go to high enough q squared, so neglecting corrections which are, say, mass of the proton over q, this can be proven at all orders, the same way that you can prove that the standard model is renormalizable. This isn't. This is mostly the fact that we know from experience that corrections to this are small. So one thing, beware that generically speaking this works, but it's not proven. So there's no proof of this. Works, but no proof. There's even cases where we know that it's actually violated. There's proof in one case, which is called Drelian, and does anyone here know what Drelian is? Q-command to leptons. So it's really saying that my final state here is just a pair of leptons. So proton-protons to a pair of leptons, L plus, L minus. That is proven, and think about this, I mean, you can view this as just being a 90-degree rotation of deep inelastic scattering. Instead of having proton-proton going to, proton-lepton going to proton-lepton, view this 90 degrees tilted, you'll get proton-proton going to lepton-lepton. So it's just a crossing, essentially a crossing symmetry compared to what happens in deep elastic scattering. So you may expect, okay, the connections, the soft physics is not the same where we discussed about initial or final state, but this is not too surprising that this is the first case you should look into, because this is very close to what we did in deep elastic scattering. Something else I wanted to say, but I can't remember what. Sigma can be computed order. I have the note somewhere here that may help. Here. Yeah. Sorry. Yeah. I think there's no real proof of violations for Dijit, I think. But in principle, I think there's no proof. I can't remember exactly in which cases there are proofs of violation. Right, that was my next point. The one difference essentially here is that if you start, well, you can have soft connections here, and these soft connections here do not have the same factorization structure as they would have in deep-inelastic scattering. So they're really, in a way, if you have something which is a soft and collinear gluon emission here, that I can put back in here. If you have a soft and collinear gluon, or just a collinear gluon in here, I can put it back in there. But if you have some crosstalks between the two protons, it's not as easy, all right? And on top of that, if you start producing quarks and gluons say that's actually supposedly a gluon. If you start producing quarks and gluon in your final state, you can also have interactions in this way. And factorizing all these soft gluons is actually not that easy in a concept. Right? I'll come back to that. So the reason I draw this picture, I'll complete this picture later in the lectures when and discussing in particular these things. All right, so I have the feeling I'm missing something, but okay, let's live with this at the moment. Yeah, at the end of the day, you want to do more than Drell-Yan at the LHC. So you hope that you're able to measure anything from Higgs to potential searches for BSM physics. And so this means that you have to compute these guys for more than one case. So as before, so keep that in mind. I'm going to come back to this over and over again during the lectures. First thing is doing a little bit of kinematics, because there's rarely a way out of this. And so remember, in E plus E minus collisions, we were having an E plus beam coming from one side, an E minus beam coming from the opposite side, same energy, collide in the center of mass, blowing out inside the final state. And you can essentially measure the energy and directions of each of the particles, and that's your natural way to describe the final state of the collision. Would that work here? Can I just measure, so LHC collides a proton and another proton in the center of mass. The center of mass of the proton-proton collision is the same as the center of mass of the detectors, the lab. Can I just measure, is it sensitive to measure all the particles by their energy and essentially direction with respect compared to the interaction point? Why? Exactly. In principle, well, in practice, this collision here is not really happening between the two protons. In practice, it's happening between the hard partons that I've taken outside of each of the protons. And since this one carries a fraction x1 and this one carries a fraction x2, generally speaking, x1 and x2 are different, which means that the real center of mass of the hard collision is boosted longitudinally, because these are partons which are collinear with beams. They're longitudinally boosted compared to the center of mass of the collision. So in practice, based on this, say PA and PB, which would be the momentum of this guy, PA is going to be x1 times square root of s over 2 times, x1 times square root of s over 2 times, and I'm essentially using that to remind you of my stupid convention, which is that's px, py, and energy. I told you I'll justify this, and don't worry, we're close to there. 0, 0, it's p going along the z direction, and pb is just going to be x2 square root of s over 2, 0, 0, minus 1, 1. So it essentially means that if you take PA plus PB, obviously it has a non-zero component against the z-axis. So this center of mass of the real collision, the real center of mass of the hard collision, is boosted along the direction of the beam. So what's the kind of variables you would want in this case? You would want something which respects this, which is invariant under this, under these boosts. So the variables that people use are, so what you're going to exploit here is essentially, instead of having a spherical symmetry, you have more like a cylindrical symmetry, all right? Where I'm very bad at drawing things in 3D, but let me nonetheless try. You're going to have something where if that's the direction of your beam, if you have a particle flying out in some direction, I'm going to use some variables which describe the properties transverse to the beam. And so for this, I'm going to introduce to transverse bits, which are going to be, on the one hand, something called pt, which is square root of px squared plus py squared. That's called the transverse momentum. And some variable phi, which is, so if you project this onto, I don't know, the plane here, I'm going to have this projected as some transverse momentum pt, which is the length of this vector, and some angle phi along the beam. Take any direction, take x for example, take this to be the x-axis of the collision. This is going to be, yes, sorry, I told you I'm bad in drawing in 3 dimensions. So I'm really going to base, so essentially pt is the size of the momentum just transversely to the beam, and phi is essentially just telling you what direction I'm going to along or around the beam. All right? Then I need, so this gives me two, this characterizes whatever happens in the plane transverse to the beam. I still need to, longitudinal. I still need to specify what happens in the direction of the beam. And for this, you're actually going to use, well, you can use also some energy variable. I'm going to call this mt, which you can define as square root of e squared minus pz squared. So e squared minus pz squared, the minus sign here is just Lorentz, right? If you say that e squared is p squared plus m squared, this is actually going to be square root of m squared plus pt squared. Okay, I'm just replacing e squared by m squared plus px, pz, py squared. So this is interesting so far. And then I still need something, so this is essentially measuring the overall magnitude, if you wish, of the longitudinal contribution. You still need something that tells me whether this, something that's related to the direction, longitudinal direction of this, and that variable is a little bit more mysterious probably. It's something called rapidity. So this is sometimes called transverse mass or energy, depending sometimes of notations, and I'm going to define something which is 1/2 log e plus pz divided by e minus pz, and that's called rapidity. First of all, that achieves what you're after, right? So if you have a particle that flows in this direction, Pz is large and positive, so Pz is very close to the energy, and in this case, this rapidity is large and positive. If there's something that is purely transverse, so with no Pz momentum, rapidity is 0. If you have something that flies far back into this region, Pz is large and negative, this is close to 0, so this is actually going to be negative. So this really goes from minus infinity here, which is what we call the backward region, and going to the forward region here with a central rapidity here. This is the type of thing you will probably face if you talk to experimentalists. There's a central thing. There's forward and backwards on both sides of the of your detector. Sometimes forward if since it's symmetric, right? Good. So far so good. So with this at hand, you can actually say that any 4-vector p mu can be written as pt times cosine phi, pt times sine phi, and then you have to invert these two guys to get the energy and pz, and that's actually mt times hyperbolic sine of y and mt times hyperbolic cosine of y. And this, and only this, is why I've chosen this stupid convention. Because you see that you typically have transverse coordinates on one side, longitudinal coordinates on the opposite side, and it really helps you. Well, in my personal opinion, do whatever you want in your own calculation. I just don't give a damn. Yeah, it's easier to have longitudinal on one side, transverse on the other, and things are better structured. I have a list of small comments here. First of all, if the particle is massless, you drop the mass, mt and pt are the same, and this becomes pt, which you can factor out. So for a massless particle, there's only one dimensional scale, which is pt, and the rest are phi, azimuthal angle, and rapidity, which describe, if you wish, the direction of your particle. The same way in an E plus E minus collision, you will have the energy of the particle or its 3 momentum for a massless particle which coincide, and then polar angles which describe its direction. Here you have the pt of the particle, which is really its momentum scale, its dimensionful scale, its energy scale, well no, energy scale, its momentum scale, and phi and y which describe its geometrical angular properties. So you can sometimes, and probably too many times, you'll hear about something called pseudo rapidity. Sometimes, well, all notations can vary, but eta, which is defined as minus log tangent theta over 2, with theta really the angle compared to the beam. So in my plot here, theta would really be the polar angle here. Which, if you try to write it down in terms of momenta, that would be 1/2 log of modulus of p, that's the 3-vector p, plus pz divided by modulus of p minus pz. Yes? No, energy is hyperbolic cosine. Well, it's not a convention. It's not really a convention. Try inverting these two equations, right? So let me give you a brief example. Try to compute, imagine I put here, try to compute the right-hand side here. You'll get log of MT factorizes and simplifies. You'll get log of cosh plus sinh divided by cosh minus sinh. And so that's exactly e to the 2y in the numerator, e to the y in the numerator, e to the minus y in the denominator. And so that's give you the log 2y divided by 1/2, that gives you 1. Yeah. Another maybe more physical way to see it, that this is bigger than this, and you know that if you want something with a mass, the energies better be bigger than pz. No, it's not a convention. It is physics here. I'll discuss a couple of things here in a second. Before that, remember where we started. We said E plus E minus collisions. We cannot use E plus E minus collisions because we have a boost along the z-axis. Now you can actually say what the boost is. If you take PA plus PB, is the overall center of mass of the collision. PA plus PB is going to have 0 transverse momentum, 0 azimuthal angle. I don't care about azimuthal angle for 0 PT is ill-defined. Then it has some energy, which is going to be related to x1, x2, and square root of s. And it also will have rapidity. So you can take PA plus PB upstairs, stick them in my definition of rapidity. What you'll find is that the rapidity of the collision is 1/2 log of x1 over x2. I'm never sure about the 1/2 here. Yes, that's 1/2. It is trivial manipulation to take the coordinates of the vector there, sum PA plus PB, and compute rapidity of PA plus PB. All right, that's the rapidity of the center of mass of your collision. So again, if x1 and x2 are the same, that's a central collision. If x1 becomes much bigger than x2, which means that guy comes with much larger longitudinal momentum than this one, the center of mass is boosted towards this side of the detector. Otherwise, in the opposite case, it's boosted toward negative rapidities. So far, so then, what happens if I make a longitudinal boost? What's going to happen to these guys? So imagine I'm just making a boost, somewhere a longitudinal boost. So I'm making a Lorentz transformation along this, a Lorentz boost along this axis here. So think about varying x1 and x2, okay? If you just vary x1 and x2, again, let me try. I maybe try to scan these notes and send them to you later when I'm coming back home. So let me again try to stick with what I have here. If you're making a longitudinal boost, I wrote that somewhere. So essentially, if you're making a longitudinal boost, say a boost delta along the z-axis, the net effect is that rapidity is just going to go into rapidity plus delta. So per se, rapidity is not, but the big thing you have here is that you start to measure, I don't know, if you start to measure any property of this final state here, which is just depends on the final state and does not depend on the initial state, differences in rapidity between these are going to be boost invariant. So any difference in rapidity delta yij, which is yi minus yj, under this transformation just remains yi minus yj. And this is important. It means that typically, if you try to compute some matrix element like this, the only dependence on x1 and x2 is just going to be overall shift of rapidity along your z-axis. That's the only dependence that you're going to get. All the other things are just going to be rapid differences, which are independent on whichever specific values of x1 and x2 have. This is not true for pseudo rapidity. So rapidity differences are invariant. If you try to make delta y, then differences in pseudo rapidity instead of rapidity, these differences are not invariant along longitudinal boost. Then there's one question. Why do you want to use this? Or what would you want to use this, in which cases would people tend to use this rather than rapidity? Yes, but that's a little bit of a fake answer, right? For massless particles, the two are equal. So if m equals 0, rapidity is equal to pseudo rapidity, and in that case, whether you use one or the other doesn't matter. My question is really, is there any case where you'd want to use eta, even though you may know that it's different from rapidity? For very energetic, yeah, if the energy is much bigger than the mass, then the correction becomes small. That's so far so good. There's actually another, much more practical example. Who's the typical person who's going to speak about pseudo rapidity and not rapidity? Experimentalists. And I mean, if I write down the 4 vector, I can compute log of e plus pz over e minus pz. Try that with some energy deposit in the calorimeter. This is much tougher, right? So experimentally, measuring an angle is way easier. You just measure an angle with respect to the beam. That's something that's almost hardwired in the detector, all right? So experimentally, this is way simpler. So more often than not, this is a variable that's going to be used in experimental context, all right? Keep in mind that there's a caveat that it's not, theoretically speaking, from a theoretical point of view, it's not as nice as rapidity, because it doesn't have the nice properties we want under boosts along the z-axis. Last 2 comments before moving to the next thing, and I'm really getting late, is, first of all, I told you can view the system really, think about a massless particle or massive, I don't care. There's really an energy scale, which is PT, or potentially PT and the mass, okay? Instead of using MT, you may use the mass, okay? It's sometimes easy because there's this easy relation between MT and the mass. So there's potentially a mass, fine, the mass of the particle, say it's in the final state, so the mass of our particle is known. You have PT, and you have 2 angular scales, which are rapidity and phi. Based on these 2 angular scales, you can define a geometric distance, which I'll call delta r ij, which you can define the same way you would define 1 minus cosine theta ij, the same way you would use theta ij or 1 minus cosine theta ij in an E plus E minus context to measure angles between pairs of particles. Here, to measure angles, I'm going to use differences in rapidity. And here I really mean rapidity. And so I can define a distance measure, an angular distance measure directly on this cylinder. And in this case, keep in mind that it's a cylinder, so phi is periodic. This is, need to watch out that if you try to compute this, there's a 2 pi periodicity for phi. The last thing is, whenever you have phase-space integrations, imagine I'm taking a particle with momentum k. Whenever you have some integration d4k 2 pi to the 4th 2 pi delta of k squared, you can, if you write it down as this expression here, so if you write this down in terms of, let me assume it's massless here again, if you write it down instead of pt, rapidity and phi, the matrix element here is 1 over 16, sorry, the matrix element, the phase space measure here is 1 over 16 pi squared dkt squared dy d phi over 2 pi. It's usually helpful to write it d phi over 2 pi because in many cases you're actually not too much sensitive to a global rotation around the z-axis. So at the end of the day, this is, in some cases, just gives you a factor of 1. Not always, but sometimes. I think I said all I wanted. Any question about kinematics? No? So the next steps are the following. I'm going to discuss a little bit more the say master formula for computing cross sections, including what it takes to be able to get this guy precisely. That's the first big bunch, including a discussion about amplitudes in that bit. The next step is going to be trying to see how that gets actually much more complicated if you're trying to doing something more generic. That's going to include also discussion about pattern shower Monte Carlo generators. And then, and given how these things go, that's probably going to be for tomorrow. I'm going to discuss how jets can be defined in this proton-proton context and carry on with hopefully an exercise on all-order resummation. So that's the roadmap between now and weekend. So let's start with discussing this master formula. Imagine that you want to make a as precise as possible calculation at the LHC. What do you need? So what are the various bits and pieces in this equation that you need in order to give me a precise answer if I'm asking you what's the cross-section for producing, I don't know, a TT bar Higgs process? What are the various bits and pieces that you need to know as well as you want, as well as you can? Yeah. PDFs. Obviously, right? It's you need to determine PDF as precisely as you want, and that's why, as we heard yesterday, there are still PhD students even working on determining PDFs, because if you don't determine PDF with a high accuracy, you don't know LHC physics with a high accuracy. I can say a few words about this. So the methodology in determining PDFs is roughly based on what I said yesterday. You have a set of data. You have a theory prediction, which is your F2 formula there, accompanied with a corresponding alternative Parisi equation, which tells you how PDF evolves. You typically find a way, whether it is sticking a function with a few parameters or using a neural network to parameterize your PDFs at some initial scale. So a PDF, let me discuss PDFs here. Some Fi, depending on x, at some scale q0 square, you parameterize this x dependence. The x dependence is completely unknown. You have to define these functions at some scale q0, either make a parameterization or use neural nets to try and get it. With the DGLAP equation at a given accuracy in QCD, you can deduce the PDFs at all values of q square. With the above formula, you can predict F2 or Drell-Yan or jet production at the LHC or a few bunch of benchmark processes that have been measured properly. And from that, you make a fit and extract. You make the best fit you can to the data and extract both the set of F. So you extract both the PDFs and their uncertainty. And once you have the PDFs and their uncertainty from what people call a global fit, I'm not going to do too many detailed calculations here. I'm actually not going to do any detailed calculation. For discussing all this, I just want to highlight the main keywords and methodologies that are important and are relevant to really understand what the basic physics goes into what you see in your everyday life at the LHC. So again, I'm just essentially trying to give you keywords and basic concepts. And so at the moment, there are mostly, well, there are different teams doing global fits. We heard yesterday about NNPDF, which is one of those. So some of them include NNPDF. The latest NNPDF set. So the more data you have, or the better your theory understanding is, you can improve your determination on PDF based on either more data, either better understanding of a theory. And so whenever you have an understanding which goes better, you have, or better determination of uncertainties, you produce a new PDF set. So there's PDFs at the moment, 3 point something, 2, maybe 1 or 2, I can't remember. Maybe even 3.3, which are provided by this group of people, and which you can then use and stick inside your equation up there. There's other groups. I think the only two I mentioned was CT. There's an old CTEC group which is for CT. I think the latest one is CT14, at least that's the one which I found yesterday. And there's another group which is MMHT. And again, these letters stand for the name of the people in the collaboration. CT doesn't stand, CT stands for CTEC, which was an old American collaboration. And some people have also said, well, we have all these different PDF sets. Let's try and give you one unique PDF set which combine all these guys with an appropriate uncertainty that encapsulates the different uncertainties between these. And so there's all the PDF people across the world decided to meet at some point and give you a recommendation, which is PDF for LHC. And this is essentially, if you want to, that's essentially the international recommendation, the community international recommendation for sticking PDFs in that expression. All right? So one thing so the methodology is the same as what I've highlighted, except that instead of doing that at leading order in alpha S, all these guys are actually next to next leading order in alpha S. So instead of having the splitting function, which is alpha S times P, it includes the alpha squared correction and the alpha cube correction. So it's 2 orders more precise than the Blackboard calculation we did yesterday. There's also all sorts of extra gory detail you probably don't want to even dream of unless you want to have nightmares for the rest of the week, but that these people have to address. For example, you do not necessarily cover the range which goes from 1 TeV to 100 TeV. You also sometimes start to have PDF which are much closer to a couple of GeVs. Once you start being close to a couple of GeVs, you also have to start to worry about the fact that at some point, at 1 GeV, you just have UDS. At 50 GeV, you have UDS-CB. And so when you go from one to the other, you start having other heavy flavor patterns inside your PDFs. And bear in mind that we were essentially saying we work in the limit of high Q square, so everything which is constant over Q square, I'm dropping. Once you start getting in, say, close to the B mass, MB over Q is not necessarily negligible. So starting to discuss about how you treat heavy flavors for charms, and in particular for bottom, is something that you have to handle if you want to make a useful prediction for the LHC. So again, this kind of details is actually not at all a detail. It's something that you need to worry. These things that I completely said we can ignore by going to IQ square is something you now have to worry about if you want to go inside prediction, inside precision kind of things. Which data set do you take into account differs between these different collaborations, and the way they treat uncertainties. Again, there's different ways to actually decide how to estimate uncertainties. It's certainly not not an easy task. Good, PDF, let's say it's covered. What else do you need? There's something simpler than PDFs here. Alpha strong. It sounds stupid, right? You say, well, alpha S is something easy. That's, well, if you want to measure, and alpha S is known, you think that alpha S is known with a high precision. Actually, with the precision that these calculations reach at the LHC today, or hope to reach in, say, the next 5 to 10 years, the uncertainty, the current uncertainty on alpha S is of the same order as the uncertainty you would get in PDFs, and maybe slightly smaller, but only slightly smaller than the uncertainty you would have on the other guys. So being able to extract alpha S robustly is also part of, again, it's going to happen later because the uncertainty is still smaller, but not that much smaller. If for the next few years, you're still fine. And this is not where people should invest their time for the next few years, unless you're probably looking forwards, which, I actually should retract this immediately because I'm personally working on some things related to extracting of alpha S. So maybe, yeah. Sorry. It's, yeah, always bad to shoot yourself in the foot. So anyway, there are inconsistencies in between different determinations of alpha S, and so this is something you might worry about, and it's good to worry about this. But in terms of really achieving precision, at the moment, the other guys are probably more important. Bear in mind that something like in the 10 years time scale, this is going to become a part of a significant part of your theory uncertainties at the end of the day. So we discussed alpha S extraction essentially based on it's based on E plus E minus event shape. There's determinations of the lattice. There's all sorts of determination. Open the PDG for a nice review in this, for example. Third, cross section. Yeah, there's only so many ingredients in this expression, right? So then there's the sigma hat. And this is what I'd like to discuss for probably a bit more time now. You want to compute amplitudes accurately, and I'll erase the right-hand side to do this. So you want to compute amplitudes accurately. That means trying to get as many orders as you want inside, well, again, as many orders as you want is again a wrong statement. As many orders as you can is probably a more accurate statement. You probably want more than what you can. But let's be realistic here and try to focus on what we can do, or what, and then essentially discuss what we want to do and hopefully can in the next near future, and not in the next 100 years. All right, so you do want a precise computation of these guys around here, right? At the moment, so this is really what amplitudes are about. And in this case, I'm really speaking about fixed order calculations. So if you want to do a fixed order calculation, you start with leading order, and let me call this bone level. Well, let me invert this. Sometimes called tree level. That's the first thing you do, right? You take the zeroth order, the lowest possible order in alpha S. Okay. Keep in mind that you sometimes have to be careful. What you mean by lowest order strongly depends on the process, all right? I don't know. Imagine you want to measure Higgs cross-sections, okay? What's the lowest order in QCD for inclusive Higgs cross-section? No. Hello. What's the power? So if I'm taking Higgs cross-section, pp to Higgs plus anything, the leading order should be alpha S to some power. What's the power there? How do you produce a Higgs at the LHC? Yeah. So it's glue to Higgs. There's mostly there's the question is actually maybe not the best example. There's mostly a question of a quark, a top loop. Let me assume that the top loop is put in an effective vertex one way or another. What's left is just glue to Higgs, and there's no strong coupling left, right? So modulo, putting aside the question of the coupling between the glue to Higgs, this is alpha S to the 0. Then next to leading order is going to be alpha S, next to next is going to be alpha squared, and so on and so forth. Imagine now I'm saying I want to produce PP imagine now I want to measure, instead of measuring the total Higgs production cross-section, I want to measure the PT of the Higgs, and I want to measure the cross-section as a function of the PT of the Higgs, of the transverse momentum of the Higgs. Again, this distribution can be expanded in a series of alpha S. What's the lowest alpha S order I can get here? Alpha S. So the alpha S to the 0 that you get here is essentially going to be, if I go back to this thing here, glue, going to a Higgs here, but the Higgs there's nothing, it's just one Higgs. In this case. So the Higgs has 0 transverse momentum because you came with 0 transverse momentum in the first place. So if you want to have a transverse momentum to the Higgs needs to get the transverse momentum. You need something else to recoil against the Higgs transverse momentum. And if you have something else to recoil against the transverse momentum, it means that you need another quark or gluon, potentially W boson or whatever. But if you have a W boson, that's not going to be alpha S, it's going to be some alpha electromagnetic. So the strongest coupling constant we have at the moment is alpha strong. So the leading order in this case is just going to be alpha S. So this is just meant to illustrate that when we say leading order, it doesn't necessarily mean just 1 power of alpha S or 0 power of alpha S. The number of powers of alpha S at the lowest possible non-trivial order does depend on your process. All right? And the list goes on. I can give you hundreds of examples like this one. It is something to keep in mind. What we mean by lowest order is really the lowest non-trivial order, and the number of powers of alpha S or alpha electromagnetic or whichever coupling does depend on the process that you're considering. So, can you do this? The real question here is it available? Is it known? Do we, I'm not asking can you sit down and do that calculation. Is it available for the community as a whole? Do we, as a community of particle physicists, know how to do bond levels? So can I get what's the set of processes? If I ask you, I don't know, TT bar Higgs plus 2 jets at leading order, is it known? Or neutralino, pair of neutralinos plus 3 jets plus 2 W boson and Higgs, and maybe toss in a TT bar pair when you're at it in a Z boson. Is it known at leading order? Virtually, yes. This is done. We know how to do this. If you add one order, that's usually what people mean by one loop. If you add one order, this is not exactly equal. Let me put that aside for the moment. I'll come back in just a second to this. If you go to the next order, you'll start having loop diagrams. Again, TT bar Higgs plus 2 jets, one loop, known, unknown. Known. In the first approximation, I'll come back to first approximation again, and I'll discuss, I'm trying just to get the big picture here. One loop calculations are known now. Virtually any process you want is known. The main limitation is essentially computation and painful. The more things you add, the more complicated it gets. But if it's just a matter of writing down the amplitude, it's known. There are ways. I'll explain the big picture in a second, because I told you I'm going to speak a little bit about amplitude. This is known. Two loops. Yeah. So two loops. Let me say a bit, okay? Some processes are known. Higgs, for example. Higgs is actually known at three loops, inclusive Higgs. A few processes are known at two loops. Mostly things which are QQ bar or two partons to a single particle are known. We start having a few processes of two incoming particles going to two outgoing particles. Again, complexity can come from two things. Complexity can come either for the number of loops you put in or the number of objects you put in, okay? The more objects you add, the more complicated the phase space, the more complicated the amplitudes, and so complexity comes from these two sides here. So this one loop thing started by computing 2 to 1 at NLO, 2 to 2, 2 to 3, 2 to 4, and so on and so forth. And once you reach 2 to some high enough n, you say, okay, the problem's solved. This is the same for two loop. We know how to do 2 to 2, or 2 to 1. We more or less know how to do 2 to 2, more or less, depending probably on the process. 2 to n is still beyond reach, okay? So this is why we heard again yesterday, probably as far as I remember, there are people trying to work on understanding next to next leading order cross-section or two-loop amplitudes. So the problem with this is that if you try, I don't know, has anyone here tried to compute a one-loop QCD calculation or something like that? No? Yes? It quickly gets complicated, right? The number, gluons interact within themselves, you can have quark loops, you can have all sorts of things. So imagine you want to make a glue going to 3 gluons, the number of graphs is huge at one loop. Glue going to 4, 5, 6, 7 gluons, the number of graphs just explodes tremendously quickly. So at some point, people said, well, first of all, they realized that the number of graphs explodes in a way which is really getting out of control. Second, they realized at the end of the day, even though the expression for all these graphs were pages long, at the end of the day, they often had very strong simplification across different graphs, at the end of the day, the answer was much shorter than all of the intermediate steps in a way. And that's usually a sign that there's something deeper, right? The same way as if you see that the electron charge is 1/3, 1/pi, sorry, not 1/3. You or probably Alex as well, you're going to say there must be something behind it. If you see that there are huge simplification compared to what you have from Feynman graphs or Feynman rules, it probably means that there's something more to the story. And so can you try and understand this, all right? And so instead of working with Feynman graphs, people tried to directly build a theory for amplitudes. All right? So in the list of references I sent you, there are, I think, 3 sets of introductory lectures on all these amplitudes. I will just give you 2 main results that I think have been key to making these 2 check marks here. The first result that people have obtained, let me see if that's the only 2 results I want. Yeah, that's the only one. It's the Brito Cachazo Feng and Witten BCFW recursion relation. And this is essentially a set of rules which allow you to write you tree amplitude in terms of smaller tree amplitudes. So if you have a tree amplitude with n particles in the final state, you're able to write in a very generic way this amplitude in terms of amplitude with less than n particles in the final state. And so using this recursion relation iteratively, that allows you to build bond level amplitudes from what you know in the past in a completely systematic way. So this result here is really key in order trying to automatize the process of computing bond level diagram. Once you have this, you can just write a piece of, either a piece of code if you, because at some point it becomes cumbersome to just, or a Mathematica package if you want, if you really want to do that. You can write a symbolic package even if you want, which is going, if you give it an amplitude, it's going to output the amplitude for that process, the tree-level amplitude, using just these recursion relation to write this amplitude down in terms of simple blocks. All right? The next thing is something that I will call the unitarity, which is called, it's not only me, the unitarity cut method. And I can't remember all of the others, is Byrne, Dixon, Dunbar, who's had missed. Byrne, Dixon, Dunbar, Kosover. What is this about? Have you heard about the optical theorem? I hope so, right? The optical theorem is essentially telling you that the imaginary part of an amplitude is, well, that you can cut through, and the square of an amplitude can be related to its the imaginary part of a more global amplitude. What it essentially boils down to is that if you cut through an amplitude, when I write a square of a graph, everything that I cut through in between the amplitude and the square amplitude is actually a list of propagators that I put on shell, because I'm saying they're in the final state. And this is, when I put these propagators on shell, the delta, the on-shell delta contribution that I get is actually the imaginary part of the propagator related to the imaginary part, the discontinuity that I would get in the propagator. If this particle was not on shell, I would consider it as the whole amplitude. Okay, so that's essentially the idea. I can cut through a particle, put it on shell, and that giving me essentially a residue around this point, which is used every day when you compute the square of an amplitude. That's actually what you're doing. What this method is actually generalizing this. This sounds trivial when I say it this way. It's actually highly non-trivial. Generalizing this this idea of putting propagators on shell to any number of cuts you may want. So you can, instead of just cutting between an amplitude and a complex conjugate, you're giving me an amplitude. I'm going to cut through it in all possible ways I can and I want, and still. That means that if you have an amplitude with one loop, I can actually cut through the loop. And if you have an amplitude with a loop and you cut through it, what do you get on the left and right side? Tree-level amplitudes. And so essentially what this is able to do is write loops in terms of trees. Why do I say it's non-trivial? Usually these things have to... I'm really swiping all technical details into the rug. For example, these things here usually work using their own formalism. Helicity spinors, for example. So all these vector nodes start with introducing you to the helicity spinor formalism. And they also assume everything to be complex. It's key, this cuts are essentially taking residues in the complex plane, taking the residue of propagators in the complex plane, and that means that you have to consider all propagators, all momenta, for example, to be complex, okay? So you will not get this if you just consider all momentum to be real. You actually derive everything, compute everything, assuming that everything can be complex, and you're applying to real stuff at the end of the day. But there are non-trivial concepts. You have to go beyond what you naively do with Feynman rules in order to get all these relations. One thing which is actually very nice, so this thing is the key to getting NLO automated. Because now that's telling me, get any one loop graph, I can actually write it down in terms of things which are tree level, and then I can apply this to get tree levels in a simple way. So this is really the key in getting NLO, again, an automating version of NLO. Give me a Lagrangian, give me a process, I'll give you the NLO amplitude. All right? Systematically. A nice thing here is that the number of trees is at most 4. Deep inside, it's related to the fact that we're living in a 4-dimensional space, and you can put at most 4 propagators on shell. In a complex plane, think of a momentum, think of the loop momentum as being a complex 4 vector, okay? A complex 4 vector, you have propagators with that 4 vector, you want to put them on shell, you want to impose residues related to these propagators, that imposes constraint close to these poles. At most 4 constraints you can impose on a 4 vector, right? Complex 4 vector in this case. So this is actually a simplification, that you don't need to consider any number of cuts, and it simplifies things greatly. And this actually does not hold at an NLO, which is why an NLO is actually a bit more complicated. All right. I think AMC at NLO uses this. MadGraph 5 AMC at NLO does. Yeah. That's part of my next. That's part of my next step. Is the amplitude the only thing you need in order to get? I don't know. I go back to my example. I'll simplify it a little bit. Imagine I want TT bar Higgs. No jets this time. TT bar Higgs at NLO. Is the amplitude the only thing I need? Okay, let me imagine I want some cross-section at NLO. This is essentially some cross-section at leading order, so Born level, plus some NLO correction. All right? Nothing serious so far. What goes, so yeah, and I'm just going to assume that this is a 2 to n process for the sake of the discussion. So TT bar Higgs would be n equals 3 in this case. What goes into here? Interference? Yeah, I was actually expecting something a bit more precise, but yeah, right. Back to what we said on Monday. Yeah, so that's the same spirit, but the operative word is real and virtual. So in this guy here, you will have 2 contributions. There's one real contribution, where say you add an extra gluon in the final state, you radiate an extra gluon in the final state, and the real is essentially a 2 to n plus 1 process, and the virtual, which is, and this is a tree graph, and there's a 2 to n 1 loop process. So essentially what we've learned from up there is that we know how to compute the matrix elements, in a way, the amplitudes, for this and that guy. Does that mean I know this? Well, you're essentially going to say, and I'm again trying to stick with what I have here, delta sigma NLO is an integration over the n plus 1 phase space of whichever, say, m squared n plus 1 real, plus an integration over, well, no, m squared is not going to cut it. Let me write this down as a delta sigma NLO real plus an integration over the n-body phase space, a delta sigma NLO virtual. And this guy contains two things. One, the amplitude, the square root of the amplitude. Two, whichever constraint you might want to impose in your final state, right? I don't know. I want the cross-section to have two tops which are within 2 units of rapidity, with the PT of the top to be at least 40 GeV, and the PT of the Higgs to be at least 100 GeV, all right? All sorts of cuts you may dream of. Or, I don't know, this cross-section, I want to measure something differential. I want to measure the PT of the Higgs in TT bar Higgs events. So I'm going here to impose that the PT of the Higgs is whichever PT I want to measure at, or the PT of the Higgs is somewhere, all right? So this contains both the matrix element, and so far so good. Matrix element we know how to get. Both the one loop, both the tree level for 2 to n plus 1 and the virtual one, and then you would need to impose any constraint that you want, because you impose cuts, you want differential distribution, you want God knows what you want beside an inclusive number. That's not necessarily easy. Even though I can give you an analytic expression for the amplitude that goes here and there, doing this integration is not necessarily trivial. It's actually highly non-trivial. Generically, if I'm telling you, can you compute that for any possible set of cuts I'm going to give you? The answer is probably no. You'll have to do that numerically, all right? And the minute you do that numerically, you hit a problem. What happens with these two guys? They diverge. So first of all, there's an assumption I've made here, which is everything I'm considering, all the observables I'm considering are infrared and collinear safe. Meaning at the end of the day, this is really finite, right? This is calculable. Infrared and collinear unsafe goes into someone else's lectures, if they want. So the idea here is really to do these integrations numerically, and the way you're going to do these integrations numerically is by generating events. All right? So you're going to have codes, programs, which are going to give you events, simulate events, and by simulating events, essentially simulating the phase space and the matrix element, giving you events that sample your phase space appropriately weighted so that you get the matrix element in as well. On which you're getting events on which you're going to be able to impose any possible set of cuts you want associated with your observable. All right? So this is where fixed order matrix element Monte Carlo generator come in. They're essentially giving you events which sample this phase space on which you can do whichever final state measurement you want. Generic purpose final state, if you wish. Not just trying to get inclusive Higgs production or some fixed quantity. The main problem is really to handle divergences here. And the idea, there's several ways to do that. The idea is really, we more or less know what QCD is in the divergent region. It's soft and collinear emissions. So what you're going to do is really saying, I'm going to introduce an extra term. I'm going to introduce a term which cancels this divergence. So this is an expression. Actually, it's usually this is done at the level of the matrix element. So I think I should have really split this into matrix element and measurement function. But so really, I'm going to introduce a term which cancels this divergences here in the soft and collinear limit or soft limits, whichever, in a way that this is finite. But if I do that, I still have to add this term over on the opposite side, delta sigma NLO virtual. In this case, it should be plus some. So this is an n plus 1 body phase space. This is an n body phase space. So I'm left with some residual one body integration. Delta sigma NLO subtract. So the idea, the trick, is to find the appropriate subtraction term, approximation, which is such that I can actually, this cancels the divergences, so at the end of the day, this block is finite and this block is finite. Well, this block is finite and this block is finite as well. So each individual terms I'm getting out of my numerical Monte Carlo integration are finite. And, well, it better be easy enough so that I can actually do this calculation here, do this integration. If you can do analytically this calculation, this integration, and combine it with the virtual, it's even better, because then it means that you can, you can actually do a bit more. There's one less integration you have to do numerically. So usually this integration here, the d phi 1 integration, is usually done analytically. So this is really the spirit of Monte Carlo fixed order Monte Carlo generators. AMC at NLO is, so MatGraph AMC at NLO is one of those. There's more dedicated code. We heard about NNLO jets, which actually doing next to next, the same trick at next to next linear order. So this is more or less automated. Tools like MatGraph AMC at NLO, you really give them, this is my model with a set of Feynman rules, Lagrangian model, standard model. I'm working in the standard model. You give it a process, and it's giving you, it may take some time, but it's going to give you, to automatically generate you the appropriate code so that you can run this. Get events for this process at NLO. Different codes differ. There's POHEG, which implements a bunch of processes. There's MCFM, which implements a bunch of processes as well. MCFM is actually trying to move to an NLO now. Well, is moving to NLO now. They essentially differ by different ways of treating the subtraction terms, and this is also part of the complexity when going to next linear order. Besides just finding ways to correctly treat the amplitudes, there's also ways to correctly introduce these subtraction terms in a way that your numerical simulations of Monte Carlo events is reasonable. I only have 15 minutes. Wow. Any questions at this stage? I can probably get there. All right. Any questions on amplitudes? Yes? Say that again. Right. This is one thing I didn't. So this is all done in the massless limit. You have other. It's part of the research to actually extend these relations to include massive particles. I actually don't know exactly what the state of the art is there. So you would typically start by adding one massive particles. I think now. Nowadays, at NLO, most of the massive cases are known. Not with an arbitrary number of masses, I don't think so, but I'm not sure. To be honest, I'm not sure. I know that, yeah, this is all massless. If you start adding masses, you get extra complications, and some of it is known, some of it is unknown. I don't know what's the exact state of the art at NLO. I think for low number of masses, everything is known. Starting with many masses, things may become more complicated. So let me go back to my initial picture. Take the case, I don't know, Higgs Higgs projection plus TT bar, all right? Or in practice. So let me try and simplify this a little bit and say I'm going to produce a gluon and a Higgs. I want to measure the PT of the Higgs. Gluon and a Higgs is probably going to be an extra gluon here, at least. Let me try to conserve the QCD chart. So, is that what you would observe in an experiment? No way. You're going to see way more. There's essentially four things that you're going to see. First, gluons can radiate, at the very least collinearly, and they can sometimes even split into QQ bar. That core can further radiate gluons, and we see that there's essentially a collinear physics here, infrared physics, that's going to make these gluons start radiate and branch into lots of guys. Similar thing happened in initial state, right? These guys can start radiating as well. Again, infrared collinear physics. So the main reason why this happens is that the scale at which you're measuring particles at the end of the day, you're measuring particles at the hadronic scale. So whatever your final state is, it has a scale which is, say, lambda QCD or the pion mass or something along those lines. And the typical scale of the typical incoming scale is also the proton scale, okay? Once, on the other hand, the scale here is some value of Q, which is much larger than either the pion mass, than say lambda QCD, okay? And we saw already several times in the past that whenever you have separate scale, there's large phase space for radiation of infrared gluons. In this case, I've drawn collinear gluons here and collinear gluons there. And these things, as what we call typically parton showers, which can be either a final state, parton shower, a final state radiation. A final state is sometimes referred to as time-like because virtuality there is positive. Or initial state parton shower, which in this case sometimes referred to as space-like because, as we saw yesterday, Q square in deep elastic scattering is actually negative virtuality. Just note that this separation here is a little bit sketchy because it's not only collinear things, but you may also have soft gluon radiation from any color line you may have in your event, okay? Any color line is going to be the same way as a QQ bar dipole, Ni plus E minus doing QQ bar. A QQ bar dipole is radiating soft gluon at any possible angle. This any possible color line that you can draw between either initial, finite, if there were more than one gluon in the final state, or initial finite dipoles, any of these guys is going to radiate soft gluons, okay? So, this is again something that you can try to address using the same type of physics I was discussing yesterday morning, I think. No, 2 days ago, Tuesday. Using essentially factorizations of these type of emissions. We know that if you have a collinear emission, it does factorize. You can write a collinear branching here, factorize that collinear branching here from the rest of the event, and just say, I'm going to compute up to this point, and then apply a splitting function to describe how this guy here branches into the QQ bar pair. So this is something where, since in the soft limit you can factorize the two, same thing for soft gluon, you can actually write down this amplitude and then add an extra soft gluon emission on top of it, which gives you just an extra factor in the amplitude. This means that you can iteratively apply this, this adding more and more factor when you add soft and or collinear gluons, and it's again something that is naturally treated in a Monte Carlo random. It's a Markov process in a way. You just generate one particle after another, one branching after another, and this is the kind of thing that is done in part-and-shower Monte Carlos in this case. So part-and-shower Monte Carlos if you want to shorten up. One thing that you have to keep in mind is that this has a given accuracy. While the Monte Carlos I was discussing earlier say MatGraph or PowHeg or MCFM, they're giving you the exact answer for QCD at a fixed order of perturbation theory. This is not the exact QCD. This is just generating the appropriate soft and collinear gluon in a way which essentially only encapsulates the leading. So the only guarantee you have